Thank you, Dimitri, for agreeing to present us this tutorial on persistent homology computation.
Yeah, so thanks for the opportunity. As I said, I'm going to sort of give a gentle introduction. And so as such, I will repeat essentially the same thing 3 times, but with progressive levels of math maybe. And please interrupt with questions. So I want to start by kind of framing the where the problem comes from, or maybe the one of the strongest motivations for the problems. And the way to do this for persistence, the easiest way to do this is to consider the following problem. Suppose that I ask you what is the highest mountain in the world. Now, you will all tell me that it's Mount Everest. There it is, 8,850 meters. Now, suppose that I ask you what are the 10 highest mountains in the world. Anybody know the answer? No, I also didn't, so I looked it up in Wikipedia. Here's the list. Now, what's interesting in this list is number 4, mountain called Lhotse, is actually this peak right next to Everest. But what's even more interesting is that the peak next to it, called Lhotse Shar, is almost 8,400 meters tall. So it should be higher than Choyu at 8,200 meters, and yet it's not on the list. And so the question is why, right? So a mystery appears. Why is Lhotse among the highest mountains in the world, but Lhotse Shar is not? And so the way that this works in mountaineering is people define a prominence of a peak as it's the height of its summit above the lowest contour line encircling it on no higher summit, which is easier to understand as how far down you have to go before you can climb to something higher. So the prominence of this peak is this height because you have to climb down to this saddle before you can climb up to something higher. The prominence of this peak is this height because you have to climb down to this saddle before you can go to something higher. And prominence is exactly persistence, just it predates it by, well, at least 100 years, but probably more than that. So the idea is that you can take this information about the prominence of the peaks, and you can record them in a persistence diagram, which will, on the vertical axis, record the maximum of the peak. On the horizontal axis, the saddle to which you have to climb down to climb to something higher. And then, so this little peak becomes this point. The fact that it's low prominence is reflected in that it's closer to the diagonal. This peak is this point, so its prominence is its distance to the diagonal, and this peak is this point. And so now, armed with this definition, you can sort of ask for the persistence diagram of the entire elevation function on planet Earth. This is what you get, and then the list that was on the Wikipedia, it says that these are the highest mountains with prominence of at least 500 meters. So in other words, they take the points in this persistence diagram, where every point corresponds to a maximum, which is the peak of a mountain, and they report the highest 10, but up to this cutoff of 500 meters. So Lhotse was just above the cutoff, Lhotse Shar was below the cutoff, and this is why it didn't make the cut in the literal sense. Now, of course, I hope it's clear from the picture, I cut off all the peaks at prominence of below 2,800 meters, because if I plotted them all, my PDF reader would crash simply because, you know, every little bump on Everest, every little wrinkle, there's sort of no bound on how far you can resolve this. It translates into a point somewhere very close to the diagonal, but it translates into a point, right? So for example, southern summit of Mount Everest is something extremely high as Everest, but very close to the diagonal. Of course, once you have this sort of view or interpretation, you can slice and dice this diagram in different ways. So in particular, you can ask, for example, what are the mountains with the highest? Was there a question?
Yeah, there's a question from me.
Sure, please.
Yeah, so I still, I've seen this a couple of times, but I'm still puzzled about your exact definition of saddle here. What is the saddle?
So there's no definition of a saddle. For everything that I'm saying so far, all you need is the height to which you have to descend before you can ascend to something higher.
Okay.
So it so happens that this is necessarily a height of a saddle, but I haven't told you why or what, or I just sort of I said that it happens to be a saddle, but that's the only part that I'm using is that this is sort of the the height to which you have to descend before you can go somewhere higher.
Okay, so that's but why is this red one is off the chart to the left? Yeah, that
Okay.
one.
Well, so it technically extends to negative infinity,
Okay,
and I declared that this line is going to be negative infinity because I didn't want to go too far to the left.
Okay.
But that's a great question. Yeah, so I'm playing fast and loose, and this is technically a point at infinity. Very good, Sherry. Okay, Sherry wins the first prize for asking questions. So
I have one question related to
Please,
this
go ahead.
actually. So
Please.
why would it be negative infinity? So can it
yeah.
go to the saddle right next to right next to it, which would not be negative infinity, right?
Well, if you go to the saddle,
Oh, okay.
you cannot ascend to anything
you cannot
higher.
go to the something higher, right?
Right. So you have to ascend to something higher. Now, if we're talking about specifically planet Earth, you're right that negative infinity doesn't make sense because there's only so far you can descend. But in general, if you imagine this was a function of a R2, for example, right, it could extend down to negative infinity. The point is that for a global maximum, there's nothing higher to climb to, so you can keep descending until you run out of where to descend to. Great questions. Okay, so speaking of descending, that once we have this persistence diagram of the elevation, we can ask not only for the highest mountains, but we can ask for the most prominent mountains, meaning that what are the points that are farthest away from the diagonal. And here you get sort of what you would expect to get. So you get Everest, of course, but then you get Aconcagua, which is the highest point in the Americas. You get Denali, the highest point in North America. You get Kilimanjaro, highest point in Africa, and so on and so forth until number 10, Mount Elbrus, highest point in Europe. And the idea, of course, is clear, right? If you are at a peak of a continent, you have to descend all the way to the ocean before you can climb to something higher. And so this is why the continents pop out as in this view. Yes, good. Okay, so now let's try to make things slightly more technical. So I flipped the picture. So before I was looking at the maxima, now I'm going to look at the minima. And so what we're actually doing is we take a function. So this is a function over some topological space X, and we're going to sweep it with its sublevel sets. And as we sweep with a sublevel set, so we look at everything below this line, which I'm going to show in green. What's going to happen is that as we pass critical points, in this case minima and maxima, because it's a function on one-dimensional domain, as we pass a minimum, a new component is going to be created. Another component is created. So they grow at regular values, but then as we pass a minimum, another component is created. And then here, these two components merged. And so what we can say is that the component that was the younger one, the one most recently born, really merges into the older component. And so we will say that there's a pair, A3, A4. So a component born at A3 dies at A4 because it merges into something older. As we pass A5, the component born at A2 merges into A5, merges at A5 into a component that is older. So it's exactly the same idea, right? That if you climb, in this case, you climb up to something where you can descend to something lower. But the point is that we can just look at the sequence of components in these sublevel sets and extract exactly the same information. So the component that was born at A1 never dies, it lives to infinity. And so we get this persistence diagram, right? So the fact that A3 was paired with A4 now becomes this point A3, A4. A2, A5 is this point, and A1 to infinity is really this point. Right?
So your birth sequence, if you are showing that this line sweeping from down from a bottom upwards, but if you sweep this line upward from top to bottom, then you get reverse the young old definition, right?
That's right. So I would get the definition that I was using on the previous page. And it turns out you can recover information from either one of those sweeps, but that's a much more technical point that I won't get to today. But yes, you can imagine flipping this, right? So instead of looking at these sub-level sets, I could have flipped this and looked at super level sets, so everything above the line. Is that okay, Shay?
So I have a question, Dimitri.
Yeah, please.
Is the assumption that your function is convex in these cases? Because Okay.
No. These are very non-convex functions, right? In fact, for a convex function, the diagram will be boring, right? There will be just one point, because there's one global minimum and nothing else, right?
This is locally convex.
There's no such assumption either, but I would have to understand what exactly you mean.
No.
In fact, I don't even need continuity. So you can make this very, very general. I don't even need a function. A function is just a way to make things easily accessible, right? But for what I'm saying, I need a topological space, could be a graph if you like, and I need a scalar function. So it's very important that this function only takes on real values. If it was taking on vector values, then all of this goes out the window. Is that okay?
What is the notation, the 0 to h of xa1?
Right. So this is the part that so these groups are called homology groups, and I'm going to revisit them 3 times, where I will define them formally towards the end. For now, this just means components. So think of this as the components at A1 map by inclusion into components at A2, map by inclusion into components at A3, and so forth. And somehow it's in this sequence of these connected components that we're keeping track of the changes. I will make this much more precise as okay. So when you have this persistence diagram, you can slice and dice it in different ways. So the rank of this map is really how many components born before B survive until C. And you can read this information also. In this case, there are 2 components that were born before B. Well, actually, in this picture, it's a little bit boring because there are only 2 components before B, but fine. So the number of components that are born before some threshold that survive up to some threshold is going to be exactly the number of points in this quadrant, upper left quadrant, with an apex at BC. And so if I increase this higher to let's say to here, then I would exclude this point, and there would be just 1 point in this component. So that's kind of the kind of information that's recorded in the persistence diagram. You can read off. What's maybe more interesting about persistence diagrams is that they're stable to perturbations. And so let me explain this idea. So suppose that I took my red function and I perturbed it into this blue function. So I added lots of little wrinkles along the way. Well, what happened to the diagrams is that I went from the diagram with these 3 points to the diagram where there are still these 3 points, and then there are lots and lots and lots of little noisy points along the diagonal. And those are exactly like the little wrinkles that I mentioned on Everest, right? Southern summit of Everest is somewhere there. Every little bump, every little rock you could throw on has really become some point near the diagonal. And it's near the diagonal because its persistence is low, right? It appears and disappears very quickly in the sequence. And so if you look at them together, you can tell that the 2 diagrams are close. And so to make this precise, we need this notion of bottleneck distance, which says that take 2 diagrams, red and blue, and now find a matching between them that minimizes the length of the longest edge, except I'm also allowed to match points with the diagonal. And this corresponds to sort of these little wrinkles appearing, or you could completely iron them out, so you can push the noisy points into the diagonal. So you can think of the diagonal as having points with infinite multiplicity. And so now the kind of main theorem, let's say, of all of this is the stability theorem. It says that if I have 2 functions f and g that are close in infinity norm, so the maximum distance between them is bounded, then the bottleneck distance between their persistence diagrams is going to be upper bounded by this L infinity distance. So this we'll make use of this in a few slides. So just kind of, but it's, I mean, intuitively it's exactly what's depicted, right? So if I take the red function, which is nice, and then I take its noisy measurement, which is what you get in real life, which is the blue function, then the blue diagram is close to the red diagram as long as I'm allowed to match points to the diagram. Questions? Aiden, you look puzzled, which means you have a question, but you're not articulating it.
No, that's not what it means.
Okay.
It's an unknown.
What is the unknown? I see. I see. Okay, fair enough.
I'm thinking like, how are we going to use this kind of question? But
Great, fantastic
we'll
question.
get there.
So yes, how are we going to use this? Okay, so I am going to now dive into this question of what was that mysterious H that for now I said was connected components, but I will get there in 2 steps. So, okay, so we're going to talk about topology. So far I only talked about connected components. Now I will talk about topology more generally. I will not define anything. I will just do things by pictures. So topology is the study of properties of spaces under continuous deformations, which is really, you can think of a study of shapes up to stretching. So I'll say the 2 shapes are the same if I can stretch one of them and get the other shape, but I'm not allowed to cut, for example, and glue, right? And so in this picture, these 2 spaces are topologically the same because, you know, the sphere and this potato is really, you can continuously deform one into the other. But for example, the sphere and this genus 2 torus, they're different because in order for me to get from here to here, I have to somehow create these 2 holes. On the other hand, this genus 2 torus and this object are also the same because even though it has these fingers and little bumps, it's a continuous deformation that I can go from here to here. Okay, so the standard joke in this field is that you know, topologist breakfast, the donut and the coffee cup are the same thing because topologically the only feature is that there is this handle on both of them, and Wikipedia has a beautiful animation. Okay, so we will not be talking about specifically topology. We'll be talking about algebraic topology. And algebraic topology at sort of a bird's eye view, the idea is that you want to be able to tell when 2 spaces are the same or when they're different. I mean, you can imagine that if you're looking at spaces like this, it can be difficult to figure out whether they're topologically the same or different. And so the algebraic approach is take a space and assign some algebraic object to it. Maybe a group, maybe a vector space, maybe something else. And now if this assignment is invariant to the space, so if I have 2 spaces that are the same topologically, they get the same object, then I can say that if I have 2 objects that are different, then they came from 2 different spaces. And one such object is homology. So this was this H, which is this vector space of non-bounding cycles. So some way to define an algebra of cycles, and we'll do this precisely towards the end. But for now, just intuition. So if I take a torus, a donut, then homology is some way to say that this blue cycle that goes around the handle and this blue cycle are actually the same. And they are the same because there is this green cylinder that whose boundary are these 2 blue cycles. But because of this, they happen to be the same. But they're different. The blue cycles are different than this red cycle in some very, very qualitative way. And so I said that this is a vector space. The 0 of this vector space is going to be a green cycle like this because it's a boundary of something. So the little cap, the cycle that it bounds is the 0 cycle. So that's okay. Bird's eye view. The way to think of homology that's easy to, maybe easier intuitively, is that if you look at the rank of the group or dimension of the vector space, it captures things that we can understand intuitively. So the 0-dimensional homology captures the number of connected components, which is what we saw with the mountains and the function that I showed before. 1-dimensional homology captures the number of loops. 2-dimensional homology captures the number of voids. And then it continues, but we run out of words in English language because it's sort of, we don't deal with higher dimensional objects too often. And so by example, if I have this space, this is my topological space, it has 3 connected components. So its Betty 0, which is the rank of its, or dimension of its 0-dimensional homology vector space, is going to be 3. If I take an annulus, its Betty 0 is going to be 1 because it has 1 connected component, and its Betty 1 is going to be 1 because it has one loop. Okay. If I look at a torus, its Betty 0 is 1, it has 1 connected component. Its Betty 1 is 2, so it has 2 essential loops. So there was the blue cycle that we saw and the red cycle that we saw. So every other cycle can be expressed as a linear combination of them. And its Betty 2 is 1 because the torus, it's hollow inside. It's a 2-manifold, and so it's like a tire tube, right? There's nothing inside, and so there's a void. Okay. So I guess where I'm going with this is that so far I was talking only about connected components, but now we will start talking about loops, voids, and higher dimensional objects. Questions?
Maybe one I have. So can you define beta 1 and beta 2 for the first two examples? You can have voids in
Well,
those, right?
they're zero. So you can certainly define them, but they just happen to be zero. So the homology groups are defined for every well, to infinity, but they're going to be zero once you go past the dimensionality of the space, just because there's no higher order connectivity. Here the space is two-dimensional, but it so happens that it has no loops and no voids, and so beta 1 is zero and beta 2 is zero. And here beta 2 is zero. Beta 2 and everything higher is zero. Does that answer your question? Ray?
How about the third figure? What will it represent if beta 2 is equal to?
Sorry, here?
Yes, if beta 2 is equal to, is there any, like, how would it, like, what should be the like
So
structure?
the entire space, the cycle that is the entire space, that's your representative. So that's the two-dimensional cycle that represents this. So in the same way that, you know, there's a blue cycle this way and the red, those are one-dimensional cycles. Now two-dimensional cycles, you can think of them as surfaces. I mean, it's not quite right, but
yeah.
so the entire torus, its surface is the two cycle that gives you this void. Okay.
Can you explain that green circle again that you showed on the tour?
Right. So it's a vector space. So the vector space needs to have a zero. Right. I mean, just because. And so the green circle, so this guy, that's our zero, because it's a boundary of something by itself. But there are lots of such zeros, right? So if I draw a boundary anywhere else, it's also going to be zero by the same logic. And why this is precisely so, I haven't given you a definition, so this is all hand waving, of course, right? Okay. So
Question.
Sherry.
So since you are talking about vector space, I guess in the down the road you are going to talk about what is the inverse. What does that mean? Those kind of operation.
You mean if I have a map between two linear spaces, what is the?
That's right. Yeah, because the
Um,
vector space you will need to define those things, right? If from mathematical point of view.
Right. So I won't need to define an inverse, because I don't think anywhere here we will be using anything. In fact, most of the maps that we will be working with will not be invertible,
Okay.
but maybe it will come up. Yeah. Put a pin in that thought, and we can come back to it once I define things more precisely.
Okay.
Okay. So Solzhenitsyn posed Aiden's question, I don't know, 60 years ago, as follows. So topology, the stratosphere of human thought. In the 24th century, it might be possibly of use to someone. Okay, so he was off by 3 centuries, I posit, but the question is how to get there. And to get there, we have to talk about homology of data. So suppose that I have some point set in Rn. So here's a bunch of points. The question is, what is its homology? Well, if I haven't lost you completely, its homology is actually extremely boring, because it's just a whole bunch of points, right? So its homology has n connected components, or whatever, p connected components, however many points I have, and nothing else, because it's just a bunch of points. So there's nothing but connected components. But of course, the question that I'm trying to ask is, what is the homology of the space from which this point set was sampled? Can we infer that? And the answer is yes. And the solution of how to do this is to squint. So you will have to squint in order to infer this homology. And the mathematical content of the word squint is that we're going to replace points by balls of radius epsilon. So if I squint, points kind of start blurring. And for every point, I will place a ball of radius epsilon. And when I do this, you will start seeing sort of these loops appear, which are homological features. But if you can see this very closely, if the resolution of zoom allows it, then you can see that there is actually one little spurious loop here, just because of the choice of the radius that I made. So there is a little loop in there, but whether it's real or fake, it's kind of hard to tell. So I can squint a little harder. This will fill in this loop, so it will declare that it's fake, but it will create another little loop over here, because it's again another feature that is kind of transient. Because of the choice of the squinting of the radius that I made, it appears, but maybe it's not real. If I squint harder, all the loops will disappear, right? So now this is topologically just an annulus. If you look from farther away, and if you keep squinting, it remains an annulus until at some point it gets filled in completely. And so as before, I will keep track of how these homology groups change, but now instead of keeping track of how the connected components change, so this sequence is back, I will keep track of how the loops are changing as I grow balls, as I'm looking at the union of balls of radius alpha around this point set. And again, as before, it turns out you can pair these births and deaths together and record the information in the persistence diagram. So again, we'll get to probably next time how to do this computationally, but algebraically you can do this, and you get this persistence diagram that has there's a point very far away from the diagonal. It corresponds to the fact that there is one very persistent loop, one cycle. So from afar, the space looks like a circle. Then there are 10 points that kind of stand out from the diagonal, so their persistence is higher than the rest. And these 10 points correspond exactly to these 10 linkages. So each one of these loops becomes a point somewhere here. And it's because these linkages, they appeared early on, right? It's my very first time I squinted, I could see these little loops. But then it takes them a while. It's the darker gray before I fill them in. And then there's a bunch of transient features. So like the cycles that I highlighted, like this cycle and this cycle, they correspond to the points very close to the diagonal. And what follows from the stability theorem, and I will make this precise in a second, is that the persistence diagram of this point set is going to be close to the persistence diagram of the space from which I sampled this point set, namely this blue curve, or union of two blue curves. And the persistence diagram for these blue curves consists of one point that is far away from the diagonal, which corresponds to the fact that from afar, these blue curves look like a circle, and then 10 points much closer with lower persistence near the diagonal, which correspond to these 10 linkages that you see. And as before, you get one diagram per dimension. Here, I'm only drawing the one-dimensional diagram. So I was only keeping track of the loops, but I could have also kept track of connected components. Just in this case, it's not a very interesting diagram. Is this okay? So I will dive a little bit into this theorem.
Dimitri, question.
Please.
So when you squint the blue curve, do you consider it as an infinite point set and squint at every point?
That's right. So when I squint at the blue curve, I also can think of it as that I place a ball of radius epsilon around every one of the infinitely many blue points, or points in the blue curve. But this really corresponds to just thickening the curve by epsilon. Yeah. We'll take all points with epsilon away from or alpha away from the blue curve. That's right.
Yeah. Thank you.
Yep. Thanks. And maybe another thing to point out, right? These blue points in the true curve, they lie on the zero axis, right? So their birth is at 0 because they are part of the curve itself, and so it's actually the homology of this curve has 11 cycles, right? So if I were to take Betty 1 of the blue curve, it would be 11. Okay, so let's unpack this because that's a nice consequence of stability. So the idea is that if two spaces are close in Hausdorff distance, then so are their persistence diagrams. The Hausdorff distance simply says that if two spaces are at most epsilon away in the Hausdorff distance, if I take the first space and I thicken it by epsilon, it will contain all the points. So if I take the first and I thicken it by epsilon, it will contain all the points of the second space. And if I take the second, so my points, and I thicken them by epsilon, it will contain the first space, so the curve. So that's what the Hausdorff distance is. And now I can compute the persistence diagram. So this was Paul's question, I think, that for the true space, I can just start thickening the curve. So this is placing balls around every point, but this is really just thickening it. And I will get a persistence diagram in this case that just has 2 points, which corresponds to the fact that this figure 8, sideways figure 8, has 2 1 cycles. And I can do the same for the point set. I can start growing these balls, and I will get a persistence diagram that has 2 points farther away from the diagonal, and then a bunch of noisy points near the diagonal. And these noisy points, just to not make it mysterious, anytime you have, for example, an acute triangle here, it's going to generate one of these points, right? Because there's going to be one cycle that appears when the balls of the triangle touch each other, and then very quickly disappears, right? Because the triangle gets filled in. And so what you get is that the persistence diagram of the point set is close to the persistence diagram of the true space, but the persistence diagram of the true space has actually the homology of the space itself. And so if you just apply stability theorem, you can derive these this homology inference theorem that says that if you have some compact space X and Rn whose weak feature size is greater than something, so the space is nicely conditioned. It doesn't have features that are too small to resolve. And if U is your point set that is Hausdorff close to X, epsilon Hausdorff close, then you can read off the homology of this hidden space X from the persistence diagram of U. So in other words, the fact that there are 2 loops in this curve, you can read off from the fact that there are 2 blue points in this quadrant epsilon 3 epsilon. So that's sort of the homology inference. In other words, you can use this procedure in order to infer what is the homology of the space that was sampled by a point set without having access to that, only having access to the sample. And so, okay,
Dimitri,
sorry, go ahead. Yep.
Can I ask a question?
Please.
So here, you give a description of beta p, right? And what is the p here? Is that related to n, or it's just?
Sorry, this p?
Yes.
That's a dimension of the cycles that I'm looking at. So 0 were components, 1 were loops, 2 were voids, and so on. So this is the homological dimension.
But okay, so I guess I don't see a p on the right hand side. So
sorry, this should be, there should be a p here, which is, I'm looking at the p dimensional. So it's these ones, right? So if I'm looking, you're right. So that's why one should define notation. So this is meant to be number of points in the epsilon 3 epsilon quadrant in the p dimensional persistence diagram of U.
okay, yeah. So for each p, the persistence diagram is totally different.
Exactly, which is a fantastic segue into the next slide, which happens to be a pop quiz. If I can figure out how to. Okay, so I computed 3 persistence diagrams for some point set that I sampled. 1 in 0 dimension, 1 in 1 dimension, 1 in 2 dimensions. The question is, what was my point set sampling? I will give you a hint. We have seen this space already.
Can you repeat the question, Dimitri?
So I took a point sample, and I sampled from some nice topological space. I computed the persistence diagrams of this point sample. I computed 3 of them, 1 in dimension 0, so this is for connected components, 1 in dimension 1 for the loops, 1 in dimension 2 for the voids. And this is what they look like. And so my question is, what is the space that I sampled?
All right, I'm going to say it's a torus because there's something happening with beta 2.
Gray wins the prize, right? So we've seen torus as the space that has 1 connected component. It has 2 prominent loops, so its Betty 1 was 2, and it has 1 prominent void. Its Betty 2 was 1. And so this is exactly what happened. I took a bunch of points on the torus, these points in green. I computed their persistence diagrams, and then we just performed homology inference together. So Gray wins the prize, and Aiden will mail him some prize. I'm not sure what. Okay, fantastic. Does this make sense?
But can you explain the one on the right? I don't understand how that comes up or how you measure it.
Well, I would do exactly the same thing as before. So I would take these points, and I would now they sit in R3, right? So they embedded in 3-dimensional Euclidean space. And so now I will start growing balls around these points. For some pretty small radius, the the balls will cover the torus. So I will actually have something that can be retracted back to the torus, but it happens to be three-dimensional, so it will have some thickness to it. And then as I keep growing these balls, at some point they will fill in the void inside the torus. And so the radius for which they will cover the surface is this radius. So it's the birth of this point. The radius for which they fill the inside, the void inside, is the death of this point. And so that's why you have this one prominent point in the two-dimensional diagram, is because this is sampled finely enough that the gap between when the points cover the surface and when they fill the inside is, well, large enough, namely, it's exactly this gap, the distance of this point to the diagram.
So would it behave differently if your donut just had a different shape with like a tiny middle?
But the tiny, so if this part was tiny, it would affect this point. So the one of the, because it's this feature is the one-dimensional cycle. It was that red cycle that I showed, right? The red cycle translates exactly into this feature. So that's a one-dimensional feature. But the fact that it's, remember, so think of a torus as a tire tube, right? The tire tube has some inner diameter, right? For which that once my balls grow to that radius of that inner diameter, there is not going to be a void inside, right? So there will be nowhere to store the air once I replace my tire tube by the balls of that radius. And so that's the death of this point.
But what about the blue circle, which should be the top point? I mean, if the middle is filled, why would there still be a blue circle that's surviving?
The blue circle will be dead by then. You're right, but the blue circle will die before I fill the void. So the blue circle. So okay. So the tire is slightly degenerate, but imagine that the radius was varying along the tire. The blue circle would fill in at the smallest radius where I can connect, where I can fit a circle inside, because that will fill the blue circle. The void will disappear at the largest radius, at the largest thickness of the tire. So the two are different, just not in this case, because here it's a degenerate situation.
So are the y-axis in these three figures aligned? I mean, because
everything is aligned. That's right, except this point is
the,
at infinity. That's why it's thick. But otherwise, the y's are aligned. Yeah.
But the beta one, in the beta one case, there's a in the middle figure, the beta one, there's a top point
So
that
this
survives
point, so this point tells you that it was the red cycle in our previous picture that goes. So the blue cycle went sort of this way, and the red cycle goes this way. And so what this tells you is that this radius, so sort of the donut hole in the colloquial sense, is bigger than the radius inside than the thickness of the torus.
Oh, okay.
So that's right. That's right. Great question. So exactly the difference between, the death here is this diameter, or this radius rather, and the death here is this radius.
Sorry, Dimitri, just to clarify, if you looked at the persistence diagram, say for beta 1, would you know which is which? Like, I guess
No.
no,
This
right?
is purely from me knowing how I sampled this thing. Right.
Okay.
You would know that there are two of them, and you would know that one is bigger than the other, but which is which? This is yeah. That's a different story.
Is there a way to sort of? Is there a way to sort of assemble what topology your points are from by looking at multiple persistence diagrams?
Yeah, so that's an outstanding question, and it has multiple interpretations, and the answer is yes for most of them. So there are. It really depends on how you do this, but there are ways to. So one of the applications of this machinery is compute these diagrams, now postulate what your space is, and now try to find an embedding of your points into that space, which is it's not a Euclidean space, right? So this could be a torus, for example. So some space that has the same topology or topology that you expect, and try to find a map that respects this topology. So that's one interpretation. Another interpretation is a little bit more complicated. So let me not go there.
I have a quick question in terms of computational. So it seems like it's difficult to do any computation using the donut, this topology thing. But if you put in the persistence diagram, then you can do a lot of computation. Is that the idea?
So that question would require some unpacking. I mean, if I wanted to compute directly with the donut, I have to tell you how I represent the donut. And since you've seen this talk before, you know that I will go into simplicial complexes and I will triangulate and I will represent the donut this way. In order for me to compute persistence for the points, I will also have to define some simplicial complexes. So in that sense, it's no more or less difficult to work with one than the other. The point is that with the points, I don't have to have access to the true space. So I can actually work with this multiscalar object that somehow captures everything that I need to know. So maybe that's
Yeah, but I'm also thinking about your donut may not be really the good, nice shaped donut. It could be, topologically it's donut, but they can have various.
Absolutely, but then if my points are sampled from it, they can also have a pretty horrible shape, right? So it's purely how I represent it, and I mean that's actually the next topic. So maybe it's
Okay.
It's a segue. Yeah. We'll discuss computation next time, but let's get to the machinery. Okay, so Sherry started asking about computation, and the question is exactly what what we started discussing, namely how do you actually represent all of this in a computer, and how do you also define homology more precisely? And what you gathered from the discussion, right, is that I'm going to replace these continuous objects that I don't know how to represent on the computer, or that may be difficult to represent on the computer, by some discrete representation, and which in this case is going to be triangulations. And the triangulations will be called simplicial complexes. So let me define what this is. Suppose that I have some set of vertices, and this could be just any set. A simplicial complex is going to be a collection of subsets of the set of vertices that is closed under containment. So in other words, if I have some sigma that is in my complex and I have its subset tau, then tau also has to be in the complex. So on the left is a nice simplicial complex. Anytime I have a triangle, I have all three edges. Anytime I have an edge, I have both of its vertices. On the right, they are not simplicial complexes. I have a triangle, but I'm missing one of its edges. I have an edge, but one of the vertices is missing. So a simplicial complex is simply this collection of subsets that's closed under containment. And this is an abstract definition, right? So all you need is some universal set, which I happen to call vertices. And then if you take subsets of that set, either they're closed under containment or not. If they are, then it's a simplicial complex. If not, then you could call it a hypergraph, for example, right? So hypergraph doesn't have this restriction, right? You can have a triple-wise relationship, triple-wise hyperedge, but not the pairwise hyperedge. But if it's furthermore closed under containment, then it's a simplicial complex. And so, by the way of language, if sigma is a p-simplex, it means that it has p plus 1 vertices. So a vertex is a 0 simplex, an edge is a 1 simplex, a triangle is a 2 simplex, the tetrahedron is a 3 simplex, and then we run out of colloquial words. So now we will define CP to be a vector space of formal sums of p simplices. So in this complex, if I take formal sums of triangles, so to every triangle I attach a weight, a value, then that's going to be called a chain, and it's going to be in C2, right? So triangle is a 2 simplex, so C2 will consist of sums of 2 simplices. one way to think of it is that the basis for this vector space are the simplices themselves. So I can specify any element in this CP vector space by saying what is the sort of the magnitude or the component along any given simplex. And there's going to be there is a boundary operator that takes any chain, any element in CP into an element into CP minus one, and in order to define it, I just have to tell you what it does on the basis elements. And on the basis elements, it simply takes two simplex and takes it into the sum, or this alternating sum of the one simplices that are contained in its boundary. So if I take this triangle ABC, it's going to map into, well, there are signs, but let's ignore the signs for a second, into plus one edge BC, minus one edge AC, and plus one edge AB, right? So AB, AC, BC. And the signs, they're not, also shouldn't be mysterious. It's just that I need, in order to define this, I need to place consistent orientation. And so the signs take care of this orientation. So if I have ABC and I map it into AC, well, it's actually what I need is CA, because I oriented edges this way. And so this is why there's a minus one there. So it's not, there's nothing complicated there. So the content of this boundary operator is captured by a boundary matrix, right? Just by a matrix where the columns are indexed by P simplices, rows are indexed by P minus one simplices. And these matrices are extremely sparse, right? So okay, there's a sparsitude. So these matrices are extremely sparse, right? So you have P entries in the column. This should be P plus one entries in the column. This is a typo. So P plus one entries in the column. But there are millions or billions of columns and rows in the real setting. So the problem is very sparse. So far so good. Okay, then I can finally attempt to define homology precisely. So suppose that I have a simplicial complex and I have its boundary operator. It goes from CP to CP minus one. I will take the kernel of this operator. So in other words, things that don't have a boundary, right? Whose boundary is zero. And I will call those cycles. And I will denote the cycle group with ZP. So here's in blue is a cycle, right? So it's a bunch of edges. But then if I take their boundary, then the vertices will cancel, right? So this vertex will be in the boundary of this edge, and it will be in the boundary of this edge. So in fact, it will be they will be there with opposite signs, and so the value on this vertex will be zero. And so just what it looks like intuitively, right? This is sort of a loop that doesn't have a boundary. That's exactly what makes it a cycle. And then there are going to be the boundaries, which are chains, or well, actually there will be cycles that are in the image of the boundary operator in one dimension higher. And I will denote this by BP. So this red guy is a boundary because it's in the image, it's a boundary of this red pink triangle. So if I take a DP plus one, so in this case D2 operator, it will map this triangle into a sum of these edges. And so the sum of these edges, this red cycle, is a boundary. That's it. So Sherry was asking about vector spaces. So I will need kernels and images, right? So the kernel is a vector space, this image is a vector space. So everything is that's where that comes into play. And so now there's one kind of key property in all of this, namely that if I square this operator, I will get a zero. So namely, in other words, if I take a boundary of some two chain or some P plus one chain, I will get a cycle. So I will get something that doesn't have a boundary. So that's what we saw with this red triangle, right? That it itself was actually the boundary of the red triangle is a cycle. And so the fact that this is d squared is zero really means that the boundary group is going to be a subset of the cycle group. And now I can define homology formally, and it's just a quotient. I'll take the cycles and I will quotient out the boundaries. So that's what we saw before, right? The two blue cycles, the two blue circles around the torus were the same because they differed by a boundary. That's really the content of the statement. Or in this picture, the blue cycle that I drew that goes all the way around here, and this cycle are going to be homologically the same because they differ by the boundary of the triangle. And they capture exactly that there is this one essential loop in the space. Yeah.
Is this d squared 0 is because of the orientation? The matrix also has minus ones and ones.
Well, it follows from that, yeah. But you could do this over. I mean, yes, it's a
You're gonna
consequence.
say you can do it in some modulus, some group is where you're gonna.
I mean, yeah, this sort of there's an entire field of homological algebra that starts with let's take operators that have this property and then go nuts, right? But yes, in the simplicial case, it's a consequence of how we define these boundary operators. Okay, well, so now things are hopefully becoming slightly less mysterious, right? So if I wanted to compute these Betty numbers, so the rank or dimension of this HP, well, that's just a rank computation, right? I need to take the rank of the cycle group, subtract the rank of the boundary group, which is the same as take the number of simplices, subtract the rank of dp, subtract the rank of dp plus 1, and you're done. And you get exactly the Betty numbers, which will tell you what's what. Which will tell you these ranks. I'm realizing I'm running out of time. How much? I don't see my clock. How much time do I have?
4 minutes.
4 minutes. Okay, so a quick preview of what's coming, maybe, and then we will stop. Or would you rather stop now?
Up to you. We can stop now if this is a good place.
Yeah. Yeah, actually, let's stop now. The fact that the questions are slowing down means that maybe I went too fast somewhere. Okay, let me stop here, and I don't know how to jump to the slide that says that I'm stopping, so I'll just scroll there. Yeah, okay. Thanks. So you have a lot to look forward to in the next 2 weeks from now. Yeah.
Great. Thank you, Dimitri.
My pleasure.
It's definitely more accessible mathematics wise. So appreciate it.
Okay, you can stop recording and then I will were you recording this? You were recording this.